Okay. Okay. So when you run the code with Python, you can just go to the folder and find the file there, and you just type Python and write the name of the file, and it will automatically perform all the processes. But now I will show you how you can perform these operations with Jupyter Lab. In my computer, I downloaded my files to my hard disk, volumes, expansion, and files. And I will run Jupyter Lab from this folder. It shows all the Jupyter scripts I have written here, and this is the file that I am looking for. Day 1 diseases. Okay. So I will run the Jupyter file directly from here. You can also import your notebook from here, like file and or your here. From here, you can load your notebook from here and select your kernel. You will select Python. Okay, I expect you have already just added your Jupyter file here, and we will run it. I will also run from here, and I will just stop it. Not this one. So many windows. I will stop this. Okay. So it will not consume my memory and computational power. So how do I just run all of the code? I will just type kernel, restart kernel, and run all cells. It will automatically run all of the cells. And I have here put some commands, and we will do all these codes together. But while it is running, I will show you a presentation, and we'll give you information about our datasets. And let's open its case study. And I will give you more detail about the datasets we use. But first, let's talk about our datasets. So, yes, we will use 3 datasets here, and in the first dataset, we have binary class. Classes are fresh fish and infected fish. And in the fresh fish class, we have more than 450 images. And infected fish, we have more images. So we have class imbalance. Okay. In the second dataset, it's a Kaggle dataset. We have multiple classes, and I have written how many samples are present in each class. For Argolus, 3 images. For this broken antenna and rostrum, 8 images. But mostly the files are from local fish, and total 93 images. Extremely imbalanced data. And in the third dataset, we have 4 classes. And as you see, classes are again not balanced, and mostly the healthy class is dominant, and this WSSV, these are the dominant classes. So it's a hard task. The first task is relatively easy, but the other 2 data sets, they are both multi-class and heavy imbalances. So it will not be easy to predict good values for these data sets, but we have a powerful approach, transfer learning, and I will talk about it in a minute. But let's inspect a bit the data sets. This is the salmon scan data. The top row shows the healthy fishes. Okay, and visually you can see that like they don't have any harms on their bodies, or like their color is okay. But when you just check the bottom images, you see that some bleeding, or the color of their shapes is different than the healthy ones. So this is a relatively easy data set. And they use in their data sets some data augmentation steps. Okay, these are the steps they apply. Why do they perform these steps? Because they want to artificially increase their training size and introduce some variability. Because in order to perform transfer learning, you have to introduce some variability, and the more your sample size bigger, the better you predict the classes. And these are the predictions they applied for machine learning algorithms: support vector machine, decision tree, logistic regression, and naive bias. And as you see, these are the metrics like sensitivity, specificity, precision, accuracy, F1 score. And when you inspect the results, SVM is the winner. In all cases, support vector machine makes the most powerful predictions. Okay, so when we run this pipeline, we will compare our results with the results of this paper and check whether we can perform better predictions. In this paper, they didn't use transfer learning approach. They just split their data. This 1,300 images. They used this data. They just split the data into training and test sets. And when they trained data, they just predicted the classes. So these are their predictions. Okay. And in the second data set, they used a lake in Bangladesh, and they identified different diseases, and these are all different classes in our data set. But I couldn't find any good paper related to these data, so I didn't put any of the results. And the other data set, the shrimp data set, your main class is healthy class, and the other three data sets contains diseased fish, diseased shrimps. Okay, so this is the model that we will use for transfer learning. It's ResNet 50, and as you see from this 50, it contains 50 layers, total 50 layers. So in this layer, in this model, they use several convolutional, pooling, convolutional, and from this till this part, they use many convolutional and pooling part. And here you have functional classification layer, and it produces 1,000 classes. Okay, so this data set is totally unrelated with fish. This data set contains many different animals, like flowers, cars, airplanes, totally irrelevant images. But the power comes from these layers, convolution part. Why? Because it's so efficiently, it was so efficiently trained that these trained layers can really identify the edges, textures, or segmentation, and it's really important for your in your training data. So this part makes all the things for you. We will use this pre-trained data set we will freeze all of these early layers till this functional classifier 1000 part. We will use all the weights here. We will change only this part. If I train it from scratch, it will be really costly. It will be time consuming. It will take a lot of time. So I don't need to do that. So I will just replace this part. And normally in practice, if you want to really adapt your data set, normally you replace the last layers, but because it takes time and it needs some computational power, I will not do that part. But if we do that, it's called fine-tuning. You adapt your training data set or your own data set, and you unfreeze these parts, generally the last layer, and these other parts, and you change your training data with these parts, and you perform fine-tuning, and it adapts your data. This is a really popular approach and very effective in prediction, and we will do that. But only because of our limited time, I will just only replace this functional classifier thousands. Normally, this model contains 1000 classes. But I showed you here, I only have 2 classes. I only have like 5 or 6 classes, here 4 classes. How do I replace that? In the late layers, you generally put your training data and you use your classification layer. Which classification layer we can use here? Any ideas? Which activation function is used for binary classification? Binary cross entropy loss, and for that we can use sigmoid activation function for binary. But for multiple classes, we can use cross entropy loss, and we can apply softmax. Yeah? Instead of using these 1000 classes, we will just select our classes number, like 4 or 5, and we will put just here either binary cross entropy loss for binary predictions, and for multi-class, we will use softmax with cross entropy loss. Okay, so this code totally makes it for all of these steps for us. Let's check whether it works or not. The main part comes here. It's running. Yes. As you see here, it makes something important. Embedding. Do you have any idea about embedding? Like here, it takes 32 images, then again takes another one, and embed it. What does it do here? It actually takes images, and in every batch, it reads 32 batches, 32 images. Okay, and I here wrote a code, just report me in some iterations how many images you have read, and the important part, you embed them. So here, I use their numerical representations for my data sets, and it's a kind of reduction of data. I don't use all of the image data, but I use a representative data for that. It's a vector representation. And this is called as embedding, and GPT also use this embedding approach. Then after embedding my results, then it finds the classes, like here 2 classes, you have these classes, and it uses 5 cross validation. Why do I make five-fold cross-validation? I have already trained my data. I already use pre-trained data. Why do I use cross-validation? Because even though I use the pre-trained bits, I will replace this part, and 70% of my data will be training here, and I will cross-validate that part. So I will not cross-validate all of these parts. It's not possible because it's fixed, frozen. But in the final layer, I will just use 70% of my training data and apply cross-validation, five-fold cross-validation. If I don't perform cross-validation, I will get over-optimistic results, and it will not be realistic. Okay, and I split my 15% is validation set and 15% is test set. Let's go back to code. And it calculates some metrics like accuracy, macro F1, and it's around 0.97. It's nice. And it applies for different machine learning models, like the 4 models we used: support vector machine, logistic regression, naive Bayes, and the other one I don't remember. I use these machine learning algorithms and predict the results. And I also do it for other 2 data sets. And these are my results. Actually, it is faster than I thought. Anyone tried this code? How much does it take? How long does it take? It takes a lot of time. Maybe even your machine cannot compute because of memory issues, because it's really expensive in terms of computation. It's now making this part. And let's show you our predictions. It's in expansion workshop, day 1. Here in transfer learning models parts. Let's start with summary all models. Okay, so let's inspect the results. As you see, we have training, validation, tests, number of all of these data sets, and it was split as 70%, 15%, 15%. These are the cross-validation flows. I tried five-fold cross-validation for all of them, but some of the classes doesn't contain 5 samples in the class. So I forced them to do whatever, which cross-validation you can do, just do it. So for this freshwater data set, it could perform 2-fold cross-validation, and for the other data set, 3-fold cross-validation. And these are my results. The macro F1 score is 0.97 for logistic regression. This is for validation data set. And for test data set, it's 0.96 for logistic regression. And for AUC, I get 0.99, nearly 1. And test AUC, it's again safe. And AUC PR, again, it's high, near 1. So logistic regression is really effective for salmon data set. Okay, for support vector machine, for the salmon data set, I again have 0.97 and 0.99. The results are extremely good. And decision tree, this time it's a bit lower than 0.9 or lower than 0.9, but here it's 0.9. AUCPR and AUC are nice. But these 2 algorithms are much better than decision tree. And naive Bayes, again, it's not higher than 0.9. So these 2 models are more powerful. And here you see some values. It's about my numbers. They are actually 0.9, 0.99. So it's about my numbers in MEC. doesn't show you the numbers properly. So for the first data set, this logistic regression and support vector machine are powerful. Okay. For the second data set, again, let's check. Logistic regression 0.4, poor. 0.38, poor. But in AUC, it's 0.95. It's nice, good. And for test AUC 0.88, it's also okay. And the most important one, AUCPR, it is 0.8. Validation, but for test 0.57. It's not so high. Okay, for support vector machine, again, when we compare, support vector machine is a bit better in terms of AUCPR, naive bias, and logistic regression. The best one is support vector machine. Why do I check AUCPR but not AUC? As you just look to test AUC values, like 0.9, 0.9, these are high scores, but they are not realistic. Why they are not realistic? Because we have class imbalances. When you have class imbalances, it's not a good way to check AUC values. So I directly check AUCPR values. And these AUCPR values must be higher than the baseline random value. And it must be statistically significant. We will check. And for the last data set, again, when we check the AUCPR, the best performing ones is two models, logistic regression and support vector machine. But when we check their AUC values, again, they are around 0.9, but not realistic. So these are the powerful models. So in our three data sets, the first one and third one can be predicted with logistic regression and support vector machine powerfully. But the second one can be predicted more powerfully with the support vector machine. Okay. And I will show you some other figures. Let's start with salmon with comparison. These are the single results for the class. So we predicted with like logistic regression and support vector machines. Let's just inspect results of logistic regression and open this confusion matrix. This is the confusion matrix of what test? Yes. So here, this is true positive. If you just define your fresh fish as the positive class. So in among 91 of the fresh fish, I correctly identify 88 of them, high true positives. If you think your infected fish is negative, these are true negatives. So only 4 type 2 and 3 type 1 error I have. Extremely good model. Okay. Mostly correct with predictions. And inspect another one. Here. Yes. Let's inspect precision. Here, as you see, precision score for binary class is 0.99, nearly 1. It's near perfect. Okay. So it can just classify powerfully and even AUC, near perfect. So logistic regression model is powerful. Let's check, for instance, naive bias, test data, and precision recall. As you see here, precision recall is 0.9 and random AUCPR is 0.62. So because of imbalance, you must have AUCPR value greater than this random AUCPR, and it's greater, actually. So it has some predictive power. Let's inspect support vector machine and test data, precision recall. Again, the random AUCPR is 0.62 and AUCPR is much higher than this value. So indeed, it can predict. Let's inspect the freshwater results. Which one was powerful? Support vector machine. Okay. And check confusion matrix. Open the confusion matrix file. Here, normally I have more than 4 classes, but some of the classes doesn't have much data, so I eliminated them, and I only have with these 4 classes. And what you see here, in my test data, I have 12 local fish, and I can identify all of the 12 fish correctly. Here, this EUS, I correctly identify one of them, but 2 disclassified. It's error. Here, this disease, not correctly identified in any case because it's 0, and this fish with infected with this disease falsely identified as local fish. But in diagonal, as you see, I have 13, but in non-diagonal cells, I have 3 misclassified. So the model is good. Why do I list data here? Because I took the 15% of the samples as test data. That's the reason. And all of my samples have 93 samples. And let's inspect these predictions. What does it show? You will see true ID. I classified it 3 third class. And what did I predict? 3. It was indeed local fish, and I predicted local fish. Again, 3, 3. It was local fish, and I predicted local fish. Here, I have an error. Normally, it was class 1. It was broken antenna and rostrum, but I predicted as third local fish. This is an error. But mostly, I predict the classes correctly. Okay. Let's inspect the last data set, shrimp classes. Which one was powerful in shrimp data set? Again, logistic regression and support vector machine. Let's look logistic regression results. Again, as you see, diagonal parts are abundant with correct samples, like healthy ones predicted as healthy, 25 of them. Okay, these are true values. Normally, you have this total amount of healthy fish, and you predicted 25 of them. And here, it's again successful. Again, here, dominantly predicted correctly, and not so bad. And let's check the test classes curves. But this time, I will not give a single AUC and AUCPR metric because it is multi-class. In multi-class, you have to just plot AUC and AUCPR, precision recall curves for each class. So let's check class healthy. In class healthy, normally random area under curve precision recall, AUCPR stands for area under curve precision recall. It's 0.17, but I predict 0.68. It's a great prediction. Why? Because you have a huge gap here. Let's check AUC. AUC class 0. Here again, AUC is near 0.9. It's a really great prediction for healthy class. Let's check another class 1. Here, random AUCPR 0.35, and I predict 0.91. But because I have less sample for this class, I cannot say it is statistically significant. And for AUC, again, it's greater than 0.9. Check another. It concludes many samples. It includes many samples, so it can be statistically significant. Like random AUCPR 0.28, and you calculate AUCPR 0.8. Your model is performing well in this condition. And just check AUC. As you see, it is 0.9. So our model is predicting each class powerfully. And this is the macro value. Most people don't want to check AUC and AUCPR values of each classes, but they just want to have a single metric so that they can evaluate the values. For that purpose, they use like macro or micro values. Macro here just takes all of the classes AUCPR or AUC values and take the average. So here, in average, on all of the classes, normally you have randomly predict 0.25, but you predict 0.75. So your model is performing well in terms of precision recall. And let's check it for AUC. Again, here, macro AUC, your classes contribution in average terms, in terms of AUC, it's greater than 0.9. So this model is powerful. Okay, so I also predicted with my machine learning algorithm and produced the same plot, and I will show you which one is better. And you tell me. This is the predictions I get. This is the paper results. Which one is better, do you think?
Purple one.
It's support vector machine. But let's check the prediction outputs. Like here, again, support vector machine is more powerful in F1 score. Here, this is F1 score, and it is greater than 0.9 here. This is the same one.
It's the wrong graphic.
I should have my own data. Maybe it hasn't calculated yet. So maybe this is my prediction. No, this is paper prediction. I put it maybe here. Yes. This is my predictions. This is the paper predictions. Now let's compare. The first one is F1 score. Okay, the labels are same. Here, with support vector machine, I get the highest F1 score. Okay, it's in percentage, like near 90% for F1 score. But here, let's put it here. But it's here, I have 97% for support vector machine. In addition, I can also use logistic regression and I get 96% F1 score for logistic regression. But here, logistic regression performed poor. Not poor, but not so good. But here, logistic regression is powerful. Let's inspect specificity. Here, the most powerful one, support vector machine, and all the others are around 80%. But here, in specificity, as you see, again, with logistic regression and support vector machine, I have much powerful specificity values. And also, this other naive bias and the decision tree improved in terms of specificity prediction. As you see, it improved. The third one was sensitivity. Again, the most powerful one is support vector machine. And here, again, for sensitivity, this support vector machine and logistic regression perform much better. And precision, as you see, again, these two models are powerful. But here, it was like 90%, but here it was 97%. Yes, near 98%. The last metric was accuracy. Support vector machine predicted 94% accuracy. Here, again, not just support vector machine, but logistic regression is also predicting around 97%. So, not just these two machine learning models, but also the other two machine learning models predicted much better than the paper's predictions. So how could it be possible? Like, I didn't train only the fish data set. I used ResNet 50 for my training data set. I just added my training data and I just replaced the last layer with my training data set and changed the classifier from 1000 to 2 or 4, depending on my data set. And it performed well than the paper's approach. And actually, we use the same machine learning models. How could it be?
I want to ask the same.
They are same.
I want to ask the same questions. Why?
Because we use the power of transfer learning. I just showed you here. Open the slide here. The power comes from transfer learning, like these layers from starting to the last layer. It's well trained. The weights and biases are estimated correctly or powerfully. So you don't need to do this part from scratch. It's a good idea to use the weights and biases of the pre-trained models, because this part will make everything for your edge detection, segmentation, texture. It's powerful. So you don't need to train it. Okay. So you will use them and you will replace just the last layer, functional class layer, and you will replace 1000 class to class which you have in your data set. In our case, it was different. And you will put here your training data with the machine learning model you want to use. I put 4 different machine learning models. Then I use the power of transfer learning and predicted more powerfully than the other approach. Okay, so main takeaway from today, if you are interested in transfer learning and you use image data sets, then you don't need to train from scratch. You use this kind of ResNet 50 and ImageNet, this kind of data sets for your pre-trained data set. Then you just replace some layers. And again, I will just remind you that the best approach would be just unfreeze this last layer and completely replace that part with your own data. That would be fine-tuning, but in our approach, because I don't replace this layer, it's feature extraction. Like I extract the features of the models in my training, so I do feature extraction. But if I had removed this part, it would be fine-tuning. Okay, so this fine-tuning approach is extremely more popular nowadays, and you should learn it because even in our fields like transcriptomics, copy number variation, we use this transfer learning approach, and no one wants to just train all of the models from scratch. We use some powerful models for our initiative and just replace some layers. Okay. For example, with single cell data, we have like
We have
huge data set.
Past 5 talk from Microsoft.
Yes, we have 5 minutes.
No break.
Okay. Maybe I just finished, by the way.
Okay. Okay,
If
great.
there is any question about transfer learning, like you learn deep, just a minute, you learn machine learning, deep learning, transfer learning. Transfer learning and deep learning are related, but machine learning is a bit a broad term. Now you can ask. You can ask.
Thank you very much for your presentation. It was very nice. I have a question. So this, the one you have talked about, the ResNet 50, it's a combination of many algorithms, as far as I just understand it, or
No.
it's not?
It's just a data set that contains 50 layers. So I use this image data set for my training data set. I don't train from scratch. I use the pre-trained model in my model, because in deep learning, you just use the weights and biases. And I just use the saved weights and biases in the pre-trained model. I loaded it, and I replaced the last layer with my own data sets. I adjusted it, so it improved my results. That's transfer learning.
So it's like, it's an architecture, and then in that we put our inputs, and then
Yes.
we have our outputs.
Yes.
So it's a combination of some architectural
Exactly.
learning.
Exactly.
Thank you.
This approach is more powerful in like histopathology data. Like they use image data set and classify whether patient has a disease or not. It's extremely powerful than other methods. Like there are many papers, you can explore them, especially if you are interested in image data. Okay. Yeni hocam.